the unsupervised learning environment, we also introduced one particular network, which is the MaxNet. Okay, we discussed the algorithm. I asked you guys to, in fact, we discussed the algorithm, we discussed the problem, and I asked you to continue that problem for the other iterations. So I hope that you guys have done that and identified that finally the node where the maximum activation is there, that would be the winner node, right? So the maximum activation node is the winner node, right? So that's what we have understood in the MaxNet algorithm. Now we proceed with a different algorithm called Mexican hat network. Okay. Mexican hat network. It's also an unsupervised learning algorithm, basically, right? So it's also unsupervised learning follows, and you will not find any kind of learning here. So no changes of weights. Okay. You may find it interesting or curious to know why it is called a Mexican hat network. You know why it is named after a hat structure, that we will also understand that in the few minutes. So it is basically developed by Koenen. In fact, he himself has developed another network. For that, you can find that this is a base model kind of a thing. Okay, so he developed by Koenen, and it is, you can say that it is a more generalized form of network. Okay, so here what you will also find is that if you see in the MaxNet, basically it is winner node. Okay, winner node takes. So that means it is basically a competitive. Okay, in a computation, we have understood in the previous class, how do you identify a winner node? Either you do dot product or you find the distance. When you do the dot product, you look for maximum activation. When you do the distance, you try to find the minimum distance to know the winner. That's what we have understood in the competitive network. In the case of Mexican, what you will understand is that you will find that there are cooperative neighbors. Okay. They will find that cooperative neighbor nodes. Okay. Out of the box question, tell me your entrance examination is called as competitive exam, right? Hello?
Yes, sir.
Okay.
Yes, sir.
Okay. All of you are agreeing that entrance exam is a competitive exam, because only those the winners will choose the seat or whatever it is. Similarly, the games, what people play. Now, coming to CAT examination, is it a competitive or cooperative?
Sir, like if you get help from friends before the exam, then we can call it as cooperative.
During exam?
I don't think we are allowed to cheat.
Okay. No, see, don't worry. Just out of, that's why I said out of box question. So the point is that when there is a cooperation, right? When there is a cooperation among the neighbors, but the point is that it is not that all nodes would have a cooperation. Cooperation would be restricted to the neighboring nodes or the nodes with the proximity. That is called radius. That anyway we will be discussing it. So in the Mexican hat network, you will find cooperative neighbors, and you can even call them as nodes with proximity. Okay, nodes with proximity are the same nodes. You can say that the neurons connected with excitatory links. Okay, weights. Okay, so these are all cooperative neighbors. Similarly, you will also have inhibitory links. Okay, you will also find that the inhibitory links or inhibitory connections which are away from the proximity. Okay, the nodes that are away from the proximity, they will have negative weights. Okay, they will have either you can call them as the negative weights, or you can call them as the inhibitory links. You can call them as the inhibitory weights. Now, when you have such network, okay, when you have that kind of a network, now let us see how the network architecture looks. Okay, so this diagram shows your network architecture of the this particular moment, I'm just copying it. Are you able to see the network? So you can notice that there are nodes. These are all the nodes arranged in the linear fashion. Okay, as an array kind of a thing. You can see that there is a node xi. There is a node xi, and you can notice that there are connections to xi with self loop. Okay, that means connection loop to itself, and also connections from other nodes. But interestingly, you can notice that in this particular diagram, you can notice that there are nodes or neurons which are far away, right? Like this is xi minus 4, this is xi plus 4. And these neurons are not connected to xi. But if you notice, xi is having connections from xi plus 1, xi minus 1. So this means this is the radius 1. Xi minus 2, xi plus 2, which is of radius 2. Xi minus 3, xi plus 3, which is the radius 3. So I hope you are able to follow what we are discussing. There is a node. Node is having connections to itself, and also the node is having connections from its neighbors. Now the range of neighborhood. So this is the range of neighborhood. Right? So this is the range of neighborhood. So you define the range of neighborhood. So in this case, the range of neighborhood is 3. So you have the nodes coming that are connected to the this particular xi node at a range of 3 neighborhood. That means with the plus 1, with the plus xi plus 1, xi plus 2, xi plus 3 on the right side. Similarly, xi minus 1, minus 2, and minus 3 on the left side. So with the radius of 3 neighbor, the radius of 3, you have the range of neighborhood. Now in this, we can say that few connections which are of proximity, like say radius 1, I'm saying radius 1 is excitatory, and radius above, so that means 2 to 3 is inhibitory. Okay, so these are all positive weights from xi minus 1 to xi plus 1 to xi. They are positive. These two are negative. I am defining it like that. Are you able to follow what we are discussing? Hello?
Yes, sir.
Yes.
So what is happening is you have the neurons for this like this for every neuron, not only for xi. Remember, when it comes to xi plus 1, obviously it will have self loop, and with a radius of 3, it will have its neighborhood. So that means xi plus 1 will have its radius on the right side with the radius of 3, means it will have xi plus 2, xi plus 3, and xi plus 4. And obviously for xi plus 1, the positive weights would be with only xi plus 2, and the negative weights with xi plus 3 and xi plus 4. Similarly, on the right side, left side, for xi plus 1, you have Xi with the positive weight, Xi minus 1 and Xi minus 2 with the negative weights. Okay, so this is how the network is structured. And when you float this network and allow the network to converge, the network activations try to converge and represent uh, their activations in this particular mesh form. Okay, just in this form. So now you notice that the graph, the mesh graph that is shown on the slide, it actually sees that, so you have a range. Okay, you have this is actually the node, and you have certain range with the positive weights. Similarly, the slopes here or the valleys here indicate the negative weights. Okay, and then it goes flattens because it is 0 after once you cross the radius, the activation or the your neighborhood is 0. Okay, and hence you know connections. Okay, so it typically looks like the structure looks like a hat, which is called a Mexican hat, and that's the reason why the network is named after that particular architecture. Are you able to follow? Okay, so now let us see how actually the the algorithm or and remember, actually another thing is that when you notice the neurons that are arrangement, we said linear arrangement. The diagram that shows is the linear arrangement. It need not be linear. You can have rectangular arrangement. You can have grid-based arrangement. So you can have several other topologies also. That anyway we will be discussing it when we are talking about the self-organizing map. So now let us see the algorithm of the Mexican hat. Anyway, it is there in the book, but I'll just keep it for your the reference here in the slide. And then we will discuss that algorithm. It is taking some time. Just give me a moment here, it is taking some time to copy. Okay. So this is the network algorithm. You can see that there are various parameters to be initialized. One is the radius. As I've said, you have the radius to be initialized. Now you define the radius, and then you have actually when we say radius, there are two types of radius. As I've said, the radius having positive weights, or you can call them as positive reinforcement weights. Similarly, the negative, or else your inhibitory links where you have. Okay, so accordingly the connection weights need to be initialized. Then you have an input signal coming in, which is also with that you are going to calculate the activation, like how we did it for the case of MaxNet. Okay, And obviously you have initial input going as the step 0 at a initial step 0 activation. Then subsequently you calculate when the network iterates, you calculate the activations, right? And then you have the threshold, which is you are going to declare what is the number of iterations to be executed for the network. Okay. So once that is done, what we are going to do is that the parameters are to be initialized as per the this one, where there are connection weights with inhibitory weight. There are connection weights with excitatory weights, right? Depends upon the region. Once that is done, you are going to provide the input from the external signal. So that is what is x is equal to s. S is your input. Okay. Then we are going to iterate the network like how we did it in the case of MaxNet. Okay. And remember, till we reach the maximum point of iterations, the network keeps in the loop. And we are going to calculate the your net input. Remember, the formula that is shown here is for a radius of 3, what we have seen in the architecture. But in general, how your activation, okay? So activation is going to be calculated it is like this. S of it, what is given here is for your 3 inputs, but in general you can say that S of it activation is going to calculate like this. S of it is sigma k wk to xi plus k at t minus 1, like how we did it in the case of MaxNet, where this is your external input signal and this is the activations coming from neighborhood, right? This is the activations or input net input coming from the net. It is coming from the rest of the other nodes. Remember, when I say rest of the other nodes, not from all nodes. Okay, it is from the neighborhood nodes. When I say the neighborhood nodes, you are going to have nodes with positive weights, nodes with inhibitory weights, that means the negative weights. So till that radius we are going to consider. Now let us take an example of the architecture. What we have seen, you have the radius of 3. In that radius of 3, you have the first radius R1. That means for xi node, I plus 1 and I minus 1 on both sides is the only connections with the positive weights. The rest of the connection weights like xi plus 2 and xi plus 3 on the right side, xi minus 2 and xi minus 3 on the left side are with negative weights. And remember, no other weights, because for the rest of the other nodes, your activations or the weight values are 0. Okay. So this is how we are going to calculate the activation or the net input. Once net input is calculated, we are going to apply the activation function, which is your the activation function that was that we discussed for the MaxNet. The same activation function which we are going to apply for your Mexican hat also. The same activation function. So that means if your net input is positive, your output is net. F of net is equal to net. If net is positive, it is 0 otherwise, right? So the same model of activation follows, and you iterate it till we reach to a point of maximum number of iterations. Okay. So what happened is with that is that network, if you look at the MaxNet, you have only one node that is getting influenced, whereas in this case it's not only the one node but also the neighborhood. When I say the neighborhood on the positive with excitatory weights and the negative weights are inhibitory links. Till that radius, you are going to have the effect, and then for the rest of the connections, you are going to have 0 as the values. Okay. Then we will proceed with the another important algorithm called self-organizing maps. The self-organizing maps are also, especially are introduced by Kohanen, who introduced your Mexican hat algorithm. There is a specific purpose of why we are actually going for the or for what kind of applications we are going for the self-organizing maps. Okay, before I actually go to the self-organizing map, let us do this activity. I'm writing here some cities. Let me write here Jaipur, then Gandhinagar, then Mumbai, then Bangalore, Trivandrum, Chennai, then Hyderabad, Patna, Lucknow, then Chandigarh, what else? Okay, Kolkata, Delhi. So how many I have written? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so I have written about 12 cities. So I'm just saying that, look, I need two groups. Tell me the two groups. Hello, here.
So the southern part and the north
Sorry?
cities.
No, no, I don't know. I'm just telling you guys to give me two groups.
Sir, we need some basis.
No. No. I'm just asking you to give me two groups. You find a basis from the. Go ahead.
Mumbai, Bangalore, Kolkata, Delhi, Hyderabad.
1 minute. Group 1. Group 2. Yeah. What shall I write under group 1?
Mumbai.
I'm writing short forms. Okay. Mumbai.
Bangalore. Chennai. Delhi. Kolkata. And that's it in group 1. Group 2, I think we should switch to. Okay, Hyderabad, Patna, Lucknow. Chandigarh. Trivandrum. Jaipur, Gandhinagar.
Okay. That's all we have done?
Yes, sir.
Now tell me how you did it. What is this?
The group 1 consists of the metropolitan cities, like the 5 famous metros,
Hyderabad is not metro yet?
Sir, group 1, sir.
No, you told in group 2.
Sir, I'm telling the group 1 consists of the metropolitan cities.
No, what about Hyderabad?
Like Hyderabad is.
Okay, leave it. No problem. Anyway, this is the logic. Okay, you said metros. Okay, no problem. Next, anyone else? Any other?
Sir, Jaipur.
Group 1?
Yes, sir. Jaipur, Gandhinagar. Delhi, Hyderabad.
Delhi, Hyderabad.
Patna. Lucknow, Chandigarh.
In group 1?
Yes, sir.
Okay, group 2?
And then group 2, Mumbai, Bangalore. Trivandrum, Chennai. Kolkata.
Something you gave. What is the basis?
So geographical location, basically
Geographical.
northern and southern parts of India, sir.
No, how come Hyderabad and Jaipur in such case has come together?
So Hyderabad will go in group 2, sorry, sir. Rest will come in group 1 only.
Okay. Even in such case, Kolkata
Yes,
and Trivandrum, how they are in group 2?
sir.
Okay, no issue. So this is what somebody else said. Okay. Yeah. So the point I wanted to, you can have, so you can do so many things. Okay. Now tell me, if I am asking you to form 4 groups. Group 1, group 2, group 3, and group 4. Then you are, let me make it first. Group 1.
Like,
Sir, you can put based upon the alphabets.
What is it?
Like first table, like starting from A to H, you keep in one group, and from
Yeah.
I to
A
and
to?
from I to P in
No.
each.
See, no. You see. You tell me the answer.
Okay, in group 1 you write Chennai, Chandigarh, Delhi, and Hyderabad.
Okay.
Bangalore.
What happened to Bangalore? Bangalore, correct. What happened to Bangalore?
Yeah, Bangalore also, yes, sir.
Okay.
In second, we can write Kolkata and Lucknow and Jaipur.
That's all. What
And
about group
Mumbai
3?
also.
Mumbai also.
Yes, sir. In group 3. What is that? Rotterdam?
Patna, yeah.
Yes.
Okay,
So
no problem.
Patna is also, I think, in group 2.
Group 2. Okay, no problem. You tell, I'll write. Patna, then. Okay, I thought it is. Okay, you thought it is Ratna.
Nothing remaining, I think.
Okay. Then I asked you to form 4 groups, no, yeah. See,
So
I asked.
null.
See, I asked 4 groups. How can you nullify 2 groups? Okay, so think on this, all that, the point is this, you can do anyway, you can have you can build the logic. Say, take an example, northeast, southwest, and then you put, and then accordingly from the based on the geographical location you put. Otherwise, you take some metric and then do it. That's okay, no problem. So take an example in the case of group 1, somebody may say, sir, I'm taking, those which are having the IT based stuff, I'm keeping it in group 1, rest in group 2. Somebody said metros, put in group 1, group 2, or whatever it is. Whatever that you are doing is actually what we have done here is that self-organizing. So the point is, I'm not talking about the validity, accuracy of it, but the process what we have put in here is the self-organizing, wherein which the input that is given to the network is the set of patterns and the number of groups that need to be formed. That's all, nothing else. Network is given with this information only. Somebody has asked me when I gave that problem, sir, what is the basis? If I give the basis, or if I indicate to which class Jaipur belongs to, Gandhinagar belongs to, Mumbai belongs to, that becomes a supervised. Right? We are talking here about the unsupervised environment where your network is trying to learn in an unsupervised manner, where by giving the patterns, right? By giving the patterns and also the output nodes, what we are talking, what I have written here, the group 1, group 2 is the basically output nodes, or else you can even call them as the cluster nodes, right? So your input nodes, which are the patterns, the output nodes that are the clusters. Okay, so the self-organizing map, coherent self-organizing map, is the one which you are going to use for applications where you are going to perform some unsupervised activity, which is like a cluster. Now, I'll come to the point of the basis. How do we do it? Basically, when we do this, what we are doing is we are pushing taking a pattern, pushing to a particular group. Okay, that means when I take Mumbai, based on the rationality, what I'm going to push is I'm going to identify a winner cluster, right? The winner is, say, take an example. Imagine if I'm saying that the metros is the rationality, group 1 is the metros, group 2 is the non-metros. I take Mumbai, push it to group 1 because for Mumbai, winner node is group 1. Okay. Now go back to the previous class discussion. How do you identify winner? How do you identify winner? There are 2 ways, right? You identify the winner. One is the dot product, another one is the distance. Another one is the distance. So essentially, the self-organizing maps, what Kohinen has introduced, the Kohinen self-organizing map is number 1, unsupervised network or unsupervised learning. Okay, number 1. Number 2, you are going to perform a kind of a clustering, okay, activity by applying the network on the problems what you are solving. Number 3 is that you have weight adjustment here. Okay, so that means you have the learning, you have the weight adjustment here. Number 3, and it also follows your proximity features. Okay, that what we have discussed, Mexican hat. So in that way, you are going to call this as your competitive cum cooperative. Okay, competitive cum cooperative. So that means when you say that I have the learning, when I say that I have the learning, and when I say that I'm going to consider the proximity, what happens is that the weight adjustment takes place not only on winner node, but also on its neighbors. Okay, so the weight adjustment takes place not only on the winner node, but also on the the nodes that are having the proximity. Is that clear? So what happens is during the learning process, the network tries to learn things, okay, adjust itself gradually. Okay, now if you once again you go back to the this one, since initially I said I need only 2 groups, and I have given the patterns. You pick a pattern and check some rationality and push it to one group. And this is an iterative process. Remember one thing, when groups are settled during the training process, you may have here and there patterns moving here and there. But when the network settles down, finally you will have the the groups. Not for one iteration you will say that yes, my learning is done. When you can say that clustering is completed, when your final iterations are completed, you can say that yes, my learning is complete. Now, okay. Now, since we say that you have input is the patterns and your output is the clusters. Obviously, we are going to have m number of patterns and n number of clusters where n is less than m typically. Okay. So that means your m number of patterns are there in the input and n number of clusters are there in the output. And when you look at the topology of the network, you can have the linear topology, you can have mesh topology, you can have rectangular topology. There are n varieties of topologies are there for self-organizing maps. So now let us see the network, how it looks. Then we will proceed with the learning algorithm. Okay. So the network looks like this. So the network looks like this. You have n number of nodes and you have about n number of clusters. Okay, output nodes, and you have the clusters. Now, if you notice the the radius or the neighborhood region, it is similar to the way your Mexican hat looks. Okay, just I will show you that also. So you can see that the neighborhood. So imagine if you are considering this node, you have the neighborhood. If it is only one node, your neighborhood range is 0. So radius of 1, radius of 2, and radius of 3. Okay. So you define the radius. Accordingly, you identify based on the algorithm. You identify the based on the metric. You identify the the winner node. And once you identified the winner node, your weight adjustment, the learning takes place not only for the winner node but also for the neighborhood nodes. Now you can see what we have seen actually in the case of Mexican hat is the linear arrangement. Of course, even this is also a linear arrangement. If you have the nodes like this, it is a linear arrangement. Now look at the rectangular arrangement of the if you have a network, you may be having a rectangular arrangement. Even for a rectangular arrangement, if you notice, this is the 0 neighbor, this is the radius 0, and this is radius 1. So when you have a rectangular architecture or a structure or the topology with the radius 1, you can notice how many number of nodes are getting excited, or how many number of neurons are getting affected. With radius 2, and similarly and radius 3, so on, based on the the radius. And not only this topology, but also you can have hexagonal topology of the topology also is possible. Now look at the hexagonal topology network. Okay, so just here, and I will keep. So okay, then this is not rectangular. The what I have written, this is the rectangular for this. So this is the rectangular, and this is your hexagon grid. Okay, and accordingly you can notice the radius. Okay, so the self-organizing network topology, and when you say define the radius, accordingly the learning takes place not only for the winner node but also for the the neighborhood nodes. So how the network proceed is quickly we will discuss, and then we will see the algorithm probably in the next class. So number one, what happen is learning goes in unsupervised manner. So the learning goes in the unsupervised fashion. What we do is initially we initialize the weights of the connections. Once we initialize the weights, these weights serve as examples. The weights serve as examples. Then you submit other parameters. One important parameter is the radius. Then there is another parameter called learning rate. Okay. So we submit. When I say submit, provide the input. So this is the initialize, or rather I should say initialize. Okay, initialize the weights, the radius, and the learning rate. Once that is done, you submit the input. So then what happens? For every input vector and example vectors are verified for winning node. when I say verified, we said your winning node is calculated either number 1 through dot product, number 2 through distance. So what we do, either you perform the dot product between the input vector and the example vector, which is nothing but your weight vector, or else you calculated the distance between the input vector and the example vector and identify the winning node. Predominantly, we do distance calculation for self-organizing map, not the dot product, and identify the winning node. When we identify the winning node, perform learning. Okay. When we perform learning, what do we mean? We are doing weight adjustment. Okay. When you do the weight adjustment, we do it not only for winner node, that also with neighborhood nodes. Okay, based on the radius that is defined. Then you proceed. Then you go back to the input vector. That means you take the next input vector and calculate. Then perform learning. Go to the input vector, perform learning, and proceed. So imagine you have, say, take an example, 4 or 5 input vectors. You submit all 4 vectors. You complete one iteration. So once you complete, for every iteration, decrease. Remember, this is not there in the other learning algorithms, which so far we discussed. See, what happens is whenever you have the training, you keep the learning rate constant. But remember, in the case of self-organizing map, you decrease the learning rate. And also, if it is required, you reduce the radius. Okay, and then check for the convergence. Okay, so this is the steps, or this is the algorithm, or these are the steps involved in the self-organizing map. Okay, is that clear? Hello?
Yes, sir.
So now let us see. Now let us see the formal algorithm. Okay, I know that we are at at the time, but just spare for another 4 or 5 minutes. We conclude, so we can complete the topic. Instead of stopping in between, the middle. Step 6. In fact, I can copy it before the session, but the point is when I keep writing, I don't know how many slides I get it. That's okay. Okay, here we go. Okay. So the problem is that the book contains these steps not in one page. If it is one page, perhaps I would have copied straight away. So now look at the algorithm, what we discussed. The self-organizing map, you have m number of input units, and there are n output units, right? And you have p number of patterns to be trained. That means your input has p patterns. So that means we said x, but in this case it is s, s1, s2, so on, p. So initially we take a random weight matrix. We define the neighborhood. So the radius, what is the radius you want? Whether it is 1, radius of 2, then apply the learning rate. Then what we do, we proceed. So you pick each training vector. That means you take S1, perform this activity, then go to S2, perform the activity, go to S3, perform, and so on up to P. Once you do it, you have completed one iteration. That means you have done with all patterns. So now what happens for every pattern? For each pattern, you calculate between the input pattern and the example pattern, what is the distance? How do you calculate the distance? Using the square of Euclidean distance. Right. So once you do that, you calculate which is the minimum. Remember, if it is the dot product, you are doing actually maximum activation. That's why you have that max net. Here, since it is a distance, you need to do minimum. So find the minimum. So with that, you are going to identify the winner node at output. That means at the cluster. That means at the Y nodes. Once you identified the winner node based on your radius, right? Where is that R? This R. Based on that R, you are going to perform the learning. How do you performing the learning? So the new weight is equal to old weight plus your learning constant into the input and the old weight. That's all. This is how your learning is taking place. Right? So what is the new weights? The old weight plus learning constant into the input minus the old weight. That's all. That is how your learning is happening. So now we did it for one pattern. What we are supposed to do, we do it for all patterns, S1, S2, so on up to SP. Now we completed all patterns. That means one iteration is complete by step 5. Then what you are doing, you see here, you update the learning rate. Okay. So you update the learning rate. If it is required, you reduce the radius also. So this, in fact, we have discussed the backpropagation algorithm. We have seen so many other algorithms. This step, especially the adjusting the learning rate, we have not encountered. But look at the case of self-organizing map. Depending on your learning, whether you increase or decrease your learning rate, but if you want, you can reduce the radius. Then you check if you are met the condition, testing condition of stopping. If so, stop. Otherwise, you continue this till the network converges to form the clusters. So this is how self-organizing map works. We have a problem that probably we will do it in the next class. Is that okay, or shall we do the problem also?
Next class, sir.
Okay.
So actually we have our STS quiz at 5.
Okay, no issue.